indicate a large temperature spike. They could hit an explosion of steam at any minute.
Steam will come. Green energy.
For drillers, that's what it's all about. From small fissures hit earlier, a small trickle of steam appears. Then, eureka! The team breaks through. They move quickly to seal off the well. However, there may be a problem. The drill team had much higher expectations for the well.
We have a little over half of the steam that we was expecting right now of good clean steam, and we're going to go ahead and clean out another 6,300 foot to bottom. Hopefully we'll get more steam.
A day later, drilling engineers finally succeed in clearing the well and increasing steam output, enough to reach their goal of 3 megawatts, which will power 3,000 homes. It's not only difficult and expensive to drill wells. Once you complete them, they can also be dangerous. Only 9 kilometers away, another drilling team just finished clearing out an old well. They work for a newcomer to the geysers, a company called Bottle Rock. They recently purchased one of the 22 plants, and if they hit steam, the plant will start up for the first time in 17 years. But several volatile gases that occur naturally in the ground are trapped deep inside the well. If drillers open it, gases will escape into the air, putting workers at risk. The most dangerous of these gases is H2S, or hydrogen sulfide. When inhaled at high levels, it deadens the senses, and victims have no idea they're being poisoned. On average, 8 workers die a year in the United States alone. In order to safely clean out the well, the Bottle Rock team will execute a difficult and dangerous maneuver known as blowing the well. Lou Capuano is the head drilling engineer for Bottle Rock. For him, getting the plant online is more than just a job. In 1998, gas and oil were cheap, and no one could see a future for an old geothermal plant.
This plant was going to be destroyed. It was going to be blown up with dynamite.
However, Lou had a dream. He and a partner believed that there was steam at Bottle Rock when others didn't. Without the backing of an energy conglomerate like Calpine, he attracted an investment company to help buy and refurbish the plant. For 2 years, he has been preparing for this moment.
Today is the first day we're going to start up this power plant after 16 years and 6 months of being shut down. When we start up the plant today, it'll be the first time that we attempt to put any power onto the grid.
They must hit enough steam to produce 17 megawatts of power, the minimum Bottle Rock needs to begin selling electricity to California's statewide electrical grid. Before it enters the plant, the steam must be cleared of rock debris. During the process, life-threatening gases are also emitted.
Large dose of H2S can be fatal. We will be moving all the personnel to that one safe spot. We want to make sure that no one gets overtaken by any of the gases because it might be concentrated coming out. We try to pick a day that's ideal weather conditions. Today we have quite a bit of wind. It'll disperse almost immediately coming out.
If the wind suddenly shifts direction, the workers have been given a sophisticated emergency plan. Run!
When we open it, a couple of minutes of gas come out. It'll be clear, you won't be able to see much, you'll hear it, and the steam will start on a little grayish, and then it'll get white. Once it gets nice and white and clean, it's ready to go to the plant.
The evacuation is complete. The team is ready to blow the well. Workers open the wellhead. Dirty steam, hydrogen sulfide, and other impurities create a plume 30 meters high. The wind stays its course, and a specialist with a gas detector confirms that toxic gases are dispersed.
Test went real well. Cleaned up rather quickly. We only had to blow it to the atmosphere by about 15 to 20 minutes.
Workers pipe the steam to the plant, where operators anxiously await the power they need to start Bottle Rock again. If all goes well, their long wait may finally be over. Despite difficult challenges, geothermal technology works where hot rock, water, and accessibility exist. However, because less than 10% of the Earth has all three elements, it may be going nowhere.
Well, that comes back to the geology of the planet, really, in terms of where water resources are in touch with hot molten lava, and those water resources have enough permeability, it's called, in order to reach the surface. And so that's in a very few places around the world.
But what if the other 90% of the Earth's land mass could be tapped for geothermal energy?
It would provide an area 10, 15, 20 times greater than we have for current geothermal systems. It's an enormous increase.
Now, two teams of visionaries, one in France and the other in Northern California, believe they've uncovered groundbreaking technologies that could very well spread geothermal power throughout the world. This is France's Rhine Valley, known for vineyards and picturesque farms. But here in the bucolic countryside, one geothermal project is hoping to win out as the weapon of choice against global warming. The Sulz project, named for a nearby village, has struggled for 20 years to answer a question critical to the future of geothermal energy. Can the Earth's heat be harvested, not only in volcanic hotspots like Iceland and the geysers, but all over the planet? If it were possible, most countries could build geothermal plants, and the world would have a clear alternative to fossil fuel plants. The work here is based on a theory developed in the 1970s at the Los Alamos National Laboratory that eventually came to be known as Enhanced Geothermal Systems, or EGS.
EGS is a process by which we drill down into the subsurface, into hot, dry areas, fracture the rocks, put water in it, and allow the water to heat it out, and then extract it.
Sulz's mission is to complete a working EGS plant in order to show that geothermal can work all over the world. Applying the principles of EGS, engineers here have already successfully drilled 3 5-kilometer wells into hot rock, injected millions of liters of high-pressure water, and created a massive artificial reservoir similar to those found in the geysers and Iceland. Their next goal? Inject water down the center well and extract heated water from the other 2. By far, the biggest challenge facing Sulz was drilling the deep wells that EGS requires.
As you work in the deep underground, you get beaten up so much, and you have so many problems going along the way, so there's a lot of pressure for sure.
Today, that pressure is about to increase. According to temperature readings taken from below, something is blocking the flow between Sulz's second and third wells.
It might be something like a barrier between the 2 wells, which has not yet been opened by fracturing.
If they can't connect the wells, Sulz will produce 50% less power than hoped, an outcome that could damage the future of EGS technology. They need to see what is stopping the water flow deep below.
We are presently trying to investigate the underground in a new seismic experiment, which is actually taking place presently in the background.
There's only one tool for the job, a seismic sensor called a geophone.
One of the things you really have to understand is you are standing here on the surface and everything you are doing is 5 kilometers away from you. It's always relying on indirect information.
An engineer cranks open the wellhead